This is Lab 9 at Home Lab with Spring Motion, and my name is Olivia Ginn, and I'm in section MO1. The purpose of this lab was to examine the motion of a spring mass system, where the mass swings in an arc while oscillating on the spring. This motion can be predicted using the momentum principle and the energy principle. The spring mass system can be compared to extreme sports with ropes that act like springs. As a result, the computer program accurately predicts the motion of the spring, and the position graphs of the computer model and the tracker model prove to be similar. However, the tracker model lags slightly due to various resistance forces. So first on tracker, I downloaded the video of the spring being pulled to the side, and I set the origin at the fixed attachment point where the spring is attached. I then set the equilibrium length where the spring is just hanging with the mass attached to the end to be 0.7 meters. The mass of the object was 0.402 kilograms. And the frame rate for this video is 1/10.5 seconds. I then tracked the motion of the spring after it was released at every position in the time step and put this position data in an Excel file, which we will look at later when we compare this to the computational model. So now moving on to the code so that we can find our computational graph. I first set the ball's mass to be the same as the mass of the object at the end of the spring. The initial position of the ball was the first data point in the position data from tracker, and the original velocity is equal to 0. I then needed to calculate the spring constant. I found this using the frequency of the oscillating spring in tracker. The equation was frequency equals 1/2 pi times the square root of ks over m. And solving for Ks, I got a value of 6.871 Newton meters. So now, having the value of Ks, I can solve for L naught. I use the equation mg equals Ks times L minus L naught, and I found L naught to be 0.127 meters. I then set my initial conditions for Ug and Ke, which were the gravitational potential energy and kinetic energy. I chose my delta t time step to be 1/210 so it would coincide with the tracker model. I then calculated the force of the spring and the force of gravity. Using the momentum principle, I calculated F net and also updated the position of the ball. Now for the energy principle, which I used to calculate the total energy. So the first step was to find the kinetic energy and delta K. Kinetic energy was equal to half times the ball's mass times the ball's velocity squared, and delta K was the change in kinetic energy from kinetic energy initial. I then found the gravitational potential energy to be the ball's mass times negative gravity times the ball's position. Delta E was equal to delta Ke plus delta Ug, and I used these values to calculate work in delta Us, which was the change in spring potential energy. So the delta Us plus delta E gave the total energy of the system. In order to compare the tracker data with the computational model for position, I plotted an orange ball for the computational model and a blue ball for tracker so that you can see the motion of both. The graph will show position versus time of the mass in the spring. When I run the code, you can see that both balls oscillate at a similar frequency. The red represents the computational model, and the green represents the data found in tracker. Also, if you change the system to include the spring, then there is no work being done on the system, but the total change in energy would still be 0, because the kinetic energy and potential energy cancel each other out. Now for the what does it mean questions. The first question says to compare the period of oscillation you found from examining the x component of position with the period of oscillation determined from the y component of position. Do they differ? If they do differ, can you explain why? So here I plotted the x component of the position on the same graph as the y component. The period of oscillation for the y component is 1.545 seconds, and the period of oscillation for the x component is about 2 seconds. The periods are similar, although the x component is larger, which may be due to the forces of air resistance or friction. The horizontal and vertical periods are independent of each other, so that is why they do not have to be the same. The second question asks, with your new choice of system, determine the work done by the surroundings. Is the energy principle satisfied? With the new choice of system, including the mass of the ball, the earth, and the spring, there is no work being done by the surroundings because all energy is conserved within the system. This satisfies the energy principle because energy is being conserved. However, there is a possibility that there is a small amount of work being done in the system by air resistance, but we won't pay that much attention right now. The third question asks, how does changing the location of the origin change the physics of the system? Discuss the impact this change had on your plots of the 3 different types of energy in the system. Well, the physics of the system stays the same. However, the quantity for the total energy of the system does change. Potential energy would change for the adjusted origin. However, the energy plots look the same.